Okay, moving on to aldehydes and ketones. So low molecular weight aldehydes and ketones are volatile and often quite pleasant smelling. And the simplest aldehyde, which is commonly called formaldehyde or methyl aldehyde or methanol, is used as a preservative in embalming, and propanone is commonly known as acetone. It's used as a solvent and is commonly used in nail polish removers. Just have a look at a few other ones just to remind us about the naming of these molecules. If we look particularly at the ketones and remind ourselves that when we get to 5 carbons we need to add numbers into our name in order to represent the position of our carbonyl group. So in this example, the carbonyl group is at position 2, so that's going to be pentan-2-one. And this one is at position 3, so that's pentan-3-one. So how do we make aldehydes and ketones? From previous work you may remember that aldehydes and ketones are oxidation products from alcohols. So if we start out with our primary alcohol, such as ethanol, CH3CH2OH, and we oxidize that, then the first product that we get is the aldehyde, ethanol. But though our aldehydes themselves are also susceptible to oxidation, so that isn't the end of the story if you continue to have an oxidizing agent in contact with your aldehyde, and you will end up with ethanoic acid unless you remove this. If we're going to write an equation for this, we represent the oxidation and the oxygen that's doing that with square brackets and an O. And here we end up with H2O. Check that that's balanced. One there, one there. Okay, let's look at secondary alcohols. So we take something like propan-2-ol. And we treat that with an oxidizing agent, and the product there is propanone. There are no further complications with this because ketones are not susceptible to any further oxidation, and again we can represent this with an equation which you may be asked to write. Commonly the oxidation is carried out using acidified potassium dichromate and the colour change is orange to green. But if we want to prepare aldehydes, then we require some special precautions. Aldehydes can be further oxidized to carboxylic acids, as we previously said, so therefore we need to distill off the aldehyde as soon as it is formed. We need to think about why we can distill aldehydes from the reaction mixture. We need to think about what's in the reaction mixture to start with. So our reaction mixture actually contains our primary alcohol, it contains our aldehyde, which we want, and it may potentially have some carboxylic acid. I need to think about the intermolecular forces that are present in these molecules and the relative strength of these. So both the alcohol and the acid will have hydrogen bonding as the strongest intermolecular force. but the aldehyde, the strongest intermolecular force, is likely to be dipole-dipole. Okay, and again, when we're approaching questions like this, we need to state the type of intermolecular force in the compounds that we're comparing, and then we need to compare the strength. So in this case, hydrogen bonding is stronger than dipole-dipole, and therefore that will mean that the aldehyde has got a lower boiling point than the other two and can be distilled off from the reaction mixture. You need to understand some ways of distinguishing between aldehydes and ketones, and the basis of all of these tests is actually their behaviour with oxidizing agents. All aldehydes can be further oxidized to carboxylic acids, but ketones cannot be oxidized. So it's possible to use any oxidizing agent to do this. There are some common ones that can be done in test tubes that you need to learn. The first one is Fehling solution, and it's based on the reduction of copper 2+ to copper 1+, which is the same as you would use in something called the Benedict's test, which is the standard test for reducing sugars in biology. If we look at the colour change, you remember from being in the lab that Cu2+ is what is present in copper sulfate, so that's going to be blue. And copper 1+ actually comes out as a brick red precipitate. The half equations, to remind us of some redox chemistry from previously, we start off with our Cu2+, it's in an alkaline solution. These are all the species that are present, Cu2+, OH-, the copper oxide and the water, so we're going to need to do some balancing here. And that half equation, and then we have our aldehyde. Okay, so aldehyde going to the carboxylate ion here, and if we are to combine those, then we can just add them together and cancel out the electrons. Okay, our OH minuses, we've got 2 here and 3 there, so that's actually 5. Tollens reagent is the one that most students remember, and it is commonly called the silver mirror test, despite the fact that actually what's often seen is a black solid precipitate of silver. If we have our aldehyde here, and we add silver ions to it, then we will oxidize that to the carboxylic acid and we will precipitate out the silver. So this here is the silver mirror, or the black precipitate. It's important not to write, if you're ever asked to describe this, not to write silver precipitate. Silver mirror is accepted and black precipitate is accepted, but not silver precipitate. So looking at what's going on in here, we start off with our ammoniacal silver. That's reduced with 1 electron to silver and ammonia. And our aldehyde, again this is alkaline solution. And overall, we're going to need to balance up these electrons. So we've got 1 electron here and 2 electrons there. So we're going to have to do 2 times this whole equation, leading us to this. You're probably not going to get asked this in the context of the carbonyl chemistry if the exam is based on the organic chemistry. However, in an overall general paper, a practical paper, or anything where you've had to study the chemistry of silver, it will probably come up then, so it's useful to look at just for interest.